Hi, in this class I am going to explain about another topic which is a basic logarithmic circuit. Here I am going to take the circuit which is having the transistor with the terminals, collector, emitter and the base. I is the current flowing through this V0 and IC is the current flowing through this collector C, and the Q1 is the transistor here we are using, and the E is the terminal here, emitter terminal here, and the R is the resistor, and the current flowing through this is I, and the VI is the input, and the VD is equals to 0 is the difference between two input terminals, and the A is the node across the inverting terminal, and the B is the node at the non-inverting terminal, and the V0 is the output here. This is the simple network for the designing of an the equation. Here the base of transistor is kept at ground. Here the base of transistor is kept at ground. We are taking only the IC and IE are equal. IE, the current flowing through IE and the current flowing through IC are equal. The current diode equation is given as IC is equals to IS of e power q VBE by KT minus 1. So here I is equals to IE, current flowing through this I is equals to IC, that means flowing along this direction is current is IC, and IC is equals to VY by R. IC is given as I is equals to IC now, so we are putting IC in the place of an IC as VI by R. VI by R, you already know the current formula. VI is equals to V by R. So here I is equals to VI by R. We are taken here. So in the basic logarithmic circuit, we have the equation IC plus IS plus 1 is equals to e power q VBE by KT. From first equation, we have first equation as IC is equals to IS of e power k VBE by KT by minus 1. IC by IS, we can write IC by IS is equals to e power q VBE KT minus 1. So here we are taking IC by IS plus 1 from the diode current equation. We can write IC by IS plus 1 is equals to e power q VBE by KT. Here IS is a saturation current, a reverse saturation current. Here IS is a reverse saturation current, reverse saturation current. So reverse saturation current is measured in the terms of an 10 power minus 13A. So here IC by IS is equals to e power q VBE by KT. You can write like this. Ignore this plus 1 value. Why? Because it is very small here. So we can get q VBE by KT is equals to ln E IC by IS. You can take this logarithmic here, logarithmic equation here. This is taken right hand side, so we can get a logarithmic, and VBE is equals to KT by Q ln E of VI by R by S. Why? Because IC is equals to VI by R. So in the place of an IC, we can put VI by R here, and then V0 is taken as a minus VBE. Why? Because here V0 is equals to minus VBE. Why? Because here it is a negative signal, negative inverting terminal is negative. So here the current flowing through this V0 is minus IBE. So here IBE minus IBE. Why? Because IE is same as an IC. So here IBE, V0 is equals to minus VBE. So V0 is equals to, we can put minus KT by Q, logarithmic value of VI by IS or also V0 is a proportional to, this is taken as a constant. So finally V0 is proportional to ln of VI. Why? Because here IS or is small, IS and the R is small. So we can consider ln of VI. IS means reverse saturation current. It is 10 more minus 13 amperes. It is very small, so we can ignore the denominator. Ln E of Vi we can finally get from the V0. So, drawbacks of logarithmic amplifier circuit. By using the logarithmic amplifier circuit, these are the drawbacks. Here, with the change in the temperature, when there is change in temperature, IS value changes. IS value changes. That means saturation value changes. That means for every 10 degrees rise in temperature, the current value also doubles. When every 10 degrees, the current value also changes, saturation value also doubles. So this is the drawbacks. The current value doubles. Every 10 degrees Celsius, the current doubles. So the saturation, due to this saturation value, so here the drawback present in the circuit. So the IS value changes from one transistor to other transistor. The IS value is not as inequal. It is varies from one transistor to another transistor. To overcome this, temperature compensated logarithmic amplifier is used. So for avoiding the IS saturation value, IS value changes from one transistor to the other transistor. So for avoiding this, a temperature compensated logarithmic amplifier is used. So here it is a temperature compensated logarithmic amplifier. Here we are using this temperature compensated amplifier like this. Here we are using the logarithmic circuit. Here one logarithmic circuit here and another logarithmic circuit here. So it is connected to this network, and it is connected through the this output. This output is given to this resistor, this circuit, which is taken R and the R and the resistor R, and the V0 dash is the output. V01 and the V02 are the inputs to this resistor, and the output for this circuit is V0 dash. So here V0 dash is given to input to this temperature dependent resistor circuit. So here RTC, time constant, and the RF, and this is the circuit which is given to this network. So here this is a simple network. This is the simple temperature compensated logarithmic amplifier. So this, by using this circuit, very simple circuit, it is a basic logarithmic circuit. It is another basic logarithmic circuit. It is connected to V01 and V02 is connected to this network, and the output from this V0 is V0 dash, and the it is input to this temperature dependent resistance circuit. So here we have by avoiding the drawbacks which are present in the basic logarithmic amplifier, we are going to use the temperature compensated logarithmic amplifier here. So here we have an equations from the temperature compensated logarithmic amplifier. So V01, from V01 and the V01 we are getting the outputs. Here U1 is the output. So from these we have V01 is connected to the minus, source is connected to the negative. Here plus here it is connected to the V02. That means here source is V reference here. So here voltage is connected to the non-inverting terminal here. So here V01 is equals to minus kT by Q ln E of V1 by IS or V1 by IS or and the here V02 is equals to kT by Q ln E of V reference by IS or. IS means saturation current. From the logarithmic equation we have here it is a logarithmic equation. Finally V0 is equals to minus kT by Q ln E Vi by IS or. So from the basic logarithmic equation we have the basic logarithmic functions with the inverting or the non-inverting terminal. So here we are put plus and here we are putting minus here. So here source is VI here and the source is V reference. So we are simply substitute VI in the place of V as VI and the place of V is V reference here. So the output voltage of subtracted circuit is we already know about the differential amplifier. VD is equals to V1 minus V2. Here VD is V0 dash. VD is V0 dash. That means output from the circuit is V0 dash. Output from the circuit to this is the differential subtractor amplifier. Subtractor amplifier. This is the circuit for the subtractor amplifier and also it is called as a differential amplifier. So output V0 dash is equals to V02 minus V01. V02 is and V01 is this. So V02 is having value kT by Q logarithmic of Vi by ISR and the V01 have value kT by Q the logarithmic value of V reference by ISR. So we have V02 and V01. So simply we are getting the output here V0 dash. V0 dash is the subtractor circuit. So output subtractor circuit output and it is we are giving the output V0 to the subtractor circuit. So from this subtractor circuit minus kT by Q ln of V reference by ISR and plus minus becomes plus. Minus becomes plus kT by Q ln of V1 by R ISR. So here it is also minus. So why? Because from this we have minus signal now. So we are putting from the output as minus. So minus kT. V02 is minus kT by Q ln of V reference by ISR plus kT by Q ln of Vi by ISR. So from that equation we can write simply kT by Q ln of Vi by V reference. Here ISR and ISR get cancelled. Then Vi by V reference we are getting here. So this is the V0 dash. V0 dash. We have another circuit. For the output of non-inverting amplifier is given as you already know about from the non-inverting amplifier. From the first unit, non-inverting amplifier output is V0 is equals to 1 plus RF by R1. V0 is equals to 1 plus RF by R1. And we have a final equation kT by Q ln E of Vi by V reference. So we are getting simply the non-inverting amplifier as V0 is equals to 1 plus RF by R1. R1 means here from the circuit RF means RF by R1 means RTC. So in the place of an R1 we are simply putting RTC there. So here we can get an final equation V0 is equals to 1 plus RF by RTC of kT by Q ln E of Vi by V reference. So this is about a temperature compensated logarithmic amplifier. So drawback, you have a drawback by using this temperature compensated logarithmic amplifier. The drawback of using this circuit is very cost effective and also complexity is more. So why? Because the circuit complexity is very high. See here, we are using a lot of components here, a lot of the circuit here. Here, basic logarithmic, two basic logarithmic amplifiers is used here, and also along with one subtractor amplifier and along with a temperature dependent circuit. So this is the complexity of the circuit, and also cost is very effective compared to the basic logarithmic amplifier. So while using this temperature compensated amplifier, the cost is effective and the also complexity is more. So to avoid this problem, a modified logarithmic amplifier circuit is used. So for avoiding this, we are going to use the modified logarithmic amplifier. So here the next concept is instrumentation amplifier. In an instrumentation amplifier, here we have the physical quantities. The instrumentation amplifier is used to measure the physical quantities which are temperature, humidity, which are the present in the atmosphere. These are the physical quantities measured by this instrumentation amplifier. This is the amplifier which is going to measure the physical quantities which are from the environment. Here we have the transducer which is converts the quantities inputs from one form of here. This is another form of inputs. It is converted to another form by using the transducers. So these signals, these normal signals are converted to electrical signals by using the transducer. So here we have an instrumentation amplifier. We have the amplifier which amplifies the instrument physical quantities by using the instrumentation amplifiers. Finally, it displays the unit. It is about an instrumentation amplifier. Also, we have another concept. It is an AC amplifier. AC amplifier is one wants to allow only AC signals and blocks DC signals. That is, this is provided by AC amplifiers. AC amplifier. The meaning of an AC amplifier is which amplifies only, which allows only AC signals and the blocks DC signals. This is provided by AC signal. This is achieved by using an AC amplifier with a coupling capacitor. So this is achieved by an AC amplifier. AC amplifier is using the coupling capacitors while measuring the AC components in the signals. So here this AC amplifier is used to measure the AC signals, not as an DC signals. An AC signals are allows while it blocks the DC signals in the output. So this is about an AC amplifiers. In by tomorrow's class, I am going to explain another topics which is an unit 4. Okay, thank you.